Thank you very much. So, well, good morning or good afternoon or good evening, everybody. And many thanks for the organizers to giving me this opportunity to give a review on 3D modeling of stellar interiors. Of course, I'm very sorry to have to give this talk, enclosed in my little box. I would have loved really to participate to all the discussions which are certainly going on, but well, next time. Anyway. So 3D modeling of stellar interiors. So what I would like to do in this talk is, first of all, I would like to place the context of multi-dimensional simulations in a stellar context, and we'll give some example of persistent problems that require multi-simulations in stellar evolution problems. Then I think I would like to give a flavor to people who are not really used maybe to hydrodynamical simulations. I would like them to understand the challenges of developing multi-D simulations for stellar interiors. And I will describe a variety of numerical approaches that exist in our community. And then I will finish on what we call the 3-to-1 link. So first of all, general context, I would say stellar context, some persistent problems that require multi-D simulations. We have heard already a few yesterday. We'll hear more during the course of this conference. One big problem in stellar evolution, this is what we call the convective boundary mixing, which is also called overshooting or penetration, and which affects any star which develop convective envelope, like the sun, for example, and you have convective penetrating flows across the convective boundary, which can drive chemical mixing, transport of angular momentum, and is very important also for the generation of magnetic fields. You have the same for stars which develop convective cores or burning shells, convective shells, and this affects any star with masses beyond 1.2 solar mass star. And this mixing, this extra mixing, affects the size of the convective core, the age, the evolution in Hertzsprung cell diagram, surface affordances, and even late stages of evolution. And we know that the problem in 1D stellar evolution code is that this mixing is treated with some free parameters, either with arbitrary mixing, instantaneous mixing over an arbitrary width, or using a diffusion coefficient with a free parameter. We have also the what we call rotationally induced mixing and transport of angular momentum, because when you have rotation, then there is a thermal imbalance, which generates a meridional circulation, a large-scale meridional circulation, as we can see on this schematic drawing of mid-air 98. And this contributes also to mixing and to transport of angular momentum in stably stratified region. We have also internal waves which are generated at convective boundaries, like indicated here in this visualization, and this contribute as well to the mixing and to the transport of angular momentum in stably stratified region. And I put here there several, I would say, references. I didn't put everything. Anyway, the slides I think will be available, so you will have access to all those references if you want to. We have also in convective zone the transport of angular momentum, and the sun is a very good example there, because we have excellent helioseismology constraints where we know the rotational rate of the sun as a function of the radius. We know the profile, and we know that in the radiative core, the rotation is a solid body rotation, and there is differential rotation in the convective envelope. And also, this is very, I would say, typical of what we call the solar rotation. The equator is faster than the pole. To understand that theoretically, so we interpret that as the differential rotation being due to the turbulent transport of angular momentum in the convective zone due to the action of Redland stresses. And what is very important is to have a very strong connection between the convection and the rotation. The problem is that many numerical simulations are in the wrong rotational regime for solar-like conditions. Typically, they are in a high Rossby number where inertial forces dominate over the Coriolis force. This is what is called the convective conundrum. But recently, there has been 3D higher resolution MHD magneto-hydrodynamic simulations by Hota and Cusano, and this was a very recent paper in Science, where the problem could be solved because of this high resolution 3D MHD simulation. I know there is a lot of discussion about those simulations and whether this is indeed the right way or not. I think this needs to be confirmed and follow up. But those type of simulations show that to understand the solar rotation, for example, you need a very consistent picture where you need to account both for surface cooling, that is the near surface layer, and interaction between convective zone and stable layers. And this is an important point for what I will mention in the following of my talk regarding how to do 3D interior simulations of stars. Then another very complex problem, this is the double diffusive convection, which is also called, depending on the regime, semi-convection or thermohaline mixing, where instabilities can occur in a medium where you have two substances which diffuse at different rates. And usually in stars or planets, those two substances are heat, which is usually the fastest diffusive substance, and chemical elements. And if you have heat, which is stabilizing the medium, then you have what we call the salt fingers or the thermohaline mixing. And if you have heat, which is the destabilizing substance, then you can have oscillatory convection, layered convection, called also semi-convection. And this can happen, for example, above the convective core of a massive star. And this is a well-known problem for stars and planet interiors, and I would refer here to the review of Pascal Garot, recent review of Pascal Garot on this very complex process. But here I highlight those problems. There are other problems, I would say, in stellar evolution, but those are really typical problems which are anisotropic, nonlinear, inherently 3D, and therefore require multi-D description. And everybody can understand then the 1D representation, which is, I would say, a static representation of those dynamical processes in a spherical symmetry, can only be rough and can only be approximated. So this is why we need multi-D simulations. But the problem is that multi-D simulations of terra interior is a real challenge. And I will take some time here for you to understand why it's very complex. So first of all, we know that the stellar interiors are in a complex regime of non-dimension parameters like the Reynolds number. Viscosity is very small, and therefore convection is going to be turbulent there because of the very high Reynolds number. The Prandtl number, which is the ratio of viscosity to thermal diffusivity, is there very small because of the very, very small viscosity. Also, we have very different time scales. So if you look at the sun, for example, which is the template of a star with a convective envelope and a radiative core, the dynamical time scale is about 30 minutes. The convective turnover time scale is about 6 days, and the thermal time scale is about 10 to the 7 years. So you have really a wide range of characteristic time scale. Same problem for example, a 5 solar mass star, which is on the ZAMS and would be a prototype of a star with a convective core and a radiative envelope, where the dynamical time scale is less than an hour. The convective time scale is about 18 days, and the thermal time scale is orders of magnitude longer, typically 10 to the 5 years. We have also very different length scales, as you know, if you are working on stellar evolution, where the characteristic length scale of a system which is in hydrostatic equilibrium varies by orders of magnitude from the center to the star up to the surface. And here, so my favorite 5 solar mass star on the ZAMS, you can see that the pressure scale height, this blue line, varies by about 5 orders of magnitude from the center to the surface. And the density stratification is absolutely enormous, the density varies by 8 orders of magnitude from the center to the surface. Other problem is the range of Mach numbers which characterize the flows in those stars. For example, in the Sun, the typical Mach number in the envelope varies from 10 to minus 4, which is a low Mach number, to up to 0.1, close to the surface. In the core of a typical massive star, the Mach number is very low, is 10 to minus 5. And even more challenging, this meridional circulation I mentioned, which is due to the rotation in the star, is of extreme low Mach number, typically of 10 to minus 10 to 10 to minus 8. So given all those complexity, the ideal 3D simulation, so what we would love to do is, first of all, we would like to have 3D simulations which would include the whole radial structure of the star from the center to the surface for several reasons. First of all, for a star like the Sun, which has a convective envelope, because of the non-local properties of convection, we know that the surface cooling has a high impact, a very large impact on the convective properties, even down to the bottom of the convective envelope. And this follows the idea of C21 and of others. We also know that there is a dynamical interaction between the convective layers and the radiative layers, as shown, for example, by Bourgeois et al. For the generation of magnetic field, but also for the properties of rotation and differential rotation. And also, if we are interested in waves, then we would like to follow whether it's convective envelope or whether it's a massive star with a convective core. We want to follow the waves, either propagating from the bottom of the convective envelope toward the center of the star, or we would like to follow the propagation of the wave from the convective core up to the surface to have some observable signatures. Ideally, we would like also to have a full sphere, because if we want to follow meridional circulation, then which is a large scale circulation, it's much better to have the full domain. And because if you want to follow also propagation of waves, then the best basis is the spherical harmonic basis. And on a full sphere, this projection of your velocity fields, for example, is straightforward. And of course, you would like also to cover long time scales, that is several tens to hundreds of convective time scale. First of all, in order to reach what I call a pseudo steady state for convection. I'll come back to that. Also, if you want to do some statistics on the flows, like what we have been performing with Jane Pratt and collaborators regarding extreme penetrative events, but also you need to cover enough time to follow the generation and the propagation of waves, above all standing waves of low frequency, which are actually due to interference of waves which are traveling all over the radiative region, and you need some time for them to set the final amplitude. So, okay, if you want to do 3D simulations of stellar interiors, the basic hydrodynamic equations that you need to solve are the fully compressible hydrodynamics equation, which I've put here. So those are the very basic equations that you need, and you recognize. So the continuity equations, this is the equations for internal energy, or you may have also total energy equation, and you have also the momentum equation with here this very important nonlinear term, which actually drives those famous Reynolds stress that I mentioned at the beginning, which are actually associated to correlations of fluctuations of the various components of velocity, and this term is absolutely very crucial. Then for stellar interiors, you need also to be able to describe the thermal transport, which usually is radiative transport, and therefore you can do it under the diffusion approximation. For stellar interior, this is fine, and you need to have the gas opacity for that. And of course, you need to have an equation of state, characteristic of stellar interiors. Then I put here some 3 dots, because you can also add other terms to the equations you want to solve. You can ask viscous terms, or you decide to rely on what we call implicit large eddy simulations, where actually the numerical viscosity is set by truncation error of your numerical scheme. And then you can add rotation and you can add magnetic fields. So now there is an issue with the time resolution, because we have a system of equations which follow this form in blue on the top. And the standard approach is to use what we call a time explicit integration method, where the solution at time step n+1 is actually a function of the solution at time step n. But the problem is that this type of time integration is strictly limited by what we call the Courant-Friedrich levy condition, which means that the time step has to be smaller than the minimum time for the sound speed to cross a cell size. And for stability reason, then this minimum time must be strictly smaller than this, what I call the CFL time step. And to give you an idea of how strict this condition is if you look at the core boundary of a 5 solar mass star, and you assume, for example, you want to have a grid resolution which actually resolves a pressure scale height at the core boundary, which is smaller than a factor 100, so which would be a good resolution for the overshooting layers above the core, then the typical CFL time step is 3 seconds, which means that you need to have times numerical time step, which is strictly smaller than that. And if you remember, then the value of the thermal time scale in this specific star is like 10 to the 5 years. So that's a problem and that's an issue. And because all of those challenges, there has been a variety of numerical approach and of multi-decodes. And I would say that there is no single solution, there is no best approach. They are only different approaches which have advantages and which have disadvantages. And I would like to give you here an idea of all those different approaches which exist in the stellar hydro community. So first, you can decide to solve equations which are approximated, and there is a well-known approximation which is the anelastic approximation, where basically the idea is to filter out sound waves, and this allows you to use numerical time steps which are greater than the CFL time step. So this kind of relaxes the constraint, the CFL constraint. And you have many groups which have been using this anelastic approximation, and there is the ASH code, which is well known as well in the field. Then you can decide as well to use what we call low max solvers, which remove the propagation of acoustic waves, but then you can retain in the equations some compressibility effects. And here you have the Maestro code, which has been used and which is used for stellar hydro applications. Then you can use, or you can solve the fully compressible equations either using a time explicit integration, and I've put here some codes like the Flash, PROMPI, and PPM star, but this is also used by, there has been also other works, important works in the field based on codes which have no name, but are also very important by Nick Bruno and Hurlburt. And then you have a time implicit approach, where this time your solution at time step n+1 is actually a function of the solution at time step n and time step n+1, which means that you need, it's more complicated, and you need to have an integration method. And actually, this is what is used in 1D stellar evolution code, the time implicit method in 1D codes. And here we have two codes, the 7 league hydro code and the music code that we have been developing in the UN, etc. What is interesting as well is that there are different ways of defining the spatial geometry. So you can actually decide to have a box in a star, which is you use a Cartesian grid and you just look at the small cube in your star, or you can use a star in a box, which is also Cartesian grid. You can use spherical wedges using spherical coordinates, or you can use also the full sphere, which is possible with spectral methods, or you have to define complex meshes to avoid the problem at the pole. And this is, for example, what is used in the SLH code, the 7-league hydro code. So now you have also two different approaches, which is either you have what I will call ideal simulations. Ideal simulations needs that you use a simplified initial setup, for example, a polytropic structure. You use an ideal gas equation of state. Usually you impose the radiative conductivity profile, so it's not based on realistic opacities, and you impose also the energy flux, so the luminosity of your system. The advantages of this approach is that you can do a parameter study in terms of the usual, I would say, non-dimensional parameters. And you can also, thanks to this parameter study, parameter sensitivity study, learn a lot about the physics of the process that you are studying. And for example of this type of study for overshooting mixing, you can study, for example, in Capillary et al. 2019, the overshooting distance as a function of the input flux. Or you can study the overshooting distance as in chi for upward overshooting above a core, a convective core. So we can study the overshooting distance as a function of the Peckley number, which is the ratio of advection to thermal diffusivity. But the disadvantage of this approach is that the 3-to-1 link, which is the extrapolation of your results to stellar conditions and to stellar problems, is not straightforward. Then you have what I call realistic, but realistic with kind of quotes, realistic simulations, meaning that you can use initial models which are derived from 1D realistic stellar structure, which are usually calculated from 1D stellar evolution codes, using realistic equation of states. Depending on the object you're studying, you can include departure from ideal gas, you can include composition variation, etc., and including as well stellar opacities or realistic stellar opacities, the one that are used to generate your 1D stellar model. The advantages of that is that you have a realistic stratification in terms of the density of the thermal conductivity, and therefore you can derive a more direct link between your 3D simulation and the 1D model or the target star you're interested in. But there is a disadvantage, and I will spend a bit of time on that, which is the problem of thermal relaxation. So the problem of thermal relaxation, that means achieving thermal relaxation, is a well-known problem for hydrodynamical simulations which are based on realistic stellar structures. And just because the thermal time scale of stars, and I gave you some numbers at the beginning, are huge compared to the relevant dynamical time scale or the convective time scale or the mixing time scales, and therefore they are computationally unreachable for major phases of evolution like the main sequence, like helium burning. And therefore there are two different approaches to address this problem. So the first approach is to consider, or you aim with your simulations to reach a pseudo steady state, which means that you look when your system, for example, has reached a plateau or a steady state in terms of total kinetic energy. And for example, in those recent simulations by Johan Hegel, devoted to convective cores of a 3.5 solar mass star, you look at the time evolution of the density average convective velocity in the core, and here is the time in the axis. Then you have a transient phase where the velocity varies, and then at some point you reach a kind of steady state. And during the steady state, then you can calculate statistical data, statistical properties, which make sense, absolute sense, on a statistical point of view, and over several characteristic time scale, like the convective time scale. But the problem with this approach, and I've put here some references of people using that, including my groups, my collaborators, is that the final thermally relaxed state of the simulation may have different properties from the non-thermally relaxed state that you are studying. So that's a problem. And then the second approach, which is a common procedure in stellar hydro simulations, is to artificially increase the luminosity or the thermal diffusivity of your system. And the luminosity in simulations can be increased by up to a factor 10 to the 7. And of course, the obvious advantage of that is that you decrease by the same factor the thermal time scale. So you kind of accelerate your simulation, which enables the simulation to reach thermally relaxed steady state. And this has, of course, the advantage of being thermally relaxed. But the problem of that is that this enhancement process of the luminosity will change the physics of your system and pushes your simulated conditions away from your original target star. And the other problem as well is that if you're interested in internal wave, then this will change as well the properties of those waves by increasing the luminosity. And we have actually done 2D experiments very recently on a 1 solar mass star, a solar-like model, by increasing the luminosity by a factor 1, 10, and up to 10 to the 4. And looking at the velocity, the typical convective velocity, so here I show the radial velocity snapshot in a convective envelope and the radiative core, where you can see convective motions with downflows in blue and upflows in red, and you can see generation of waves in the radiative core. And here, this is the model which has a luminosity enhanced by a factor 10 to the 4. And typically, the convective velocity scales with the luminosity at the power of 1/3, which means that the convective time scale, the characteristic convective time scales, decrease accordingly, or the convective frequency varies like the convective velocity, that is increased with the luminosity. And if we look at the property of waves, so this is a work that my PhD and collaborators, so Arthur Lesault, my PhD student, has performed, and we just submitted this analysis. So if you look at the wave energy flux in the radiative core, you can see, so here this is the frequency, and here this is characterized the flux of energy of the waves. Then you can see that the waves that bears most of the energy is not in the same frequency range. So the main message, takeaway message, is that you have a shift of the spectrum towards higher frequency if you increase the luminosity. And this can be important if you are interested, for example, in the transport of angular momentum, which actually depends on the damping of the waves and therefore on the frequency of the waves. So this is something to bear in mind. So now, given all, I would say, all the different approaches, the different problems that I've highlighted, of course, despite all different approaches, different geometry, etc., it is very important for existing hydrodynamical codes to give the same answers. Because, well, it's, I think it's, of course, crucial that there is a kind of convergence of results independently of the numerical approach and of the choice of your, I would say, your best numerical scheme. And what is reassuring is that they do indeed, even for complex problems. And there has been a huge effort from several groups where actually 5 different hydrodynamical codes have been compared. Those codes are Flash, Music, ppm star, PROMPI, and SLH. And this is a paper which is on AstroPH, has been recently submitted, led by Robert Andrassy, and all those people who are involved in the development of those codes and in using those different codes. And the problem is complex. It's not the usual hydrodynamical benchmark that any hydro code should do. It's something more complex, which is related to turbulent convection and to mass entrainment in a plane parallel box. And it's a kind of simplified test of shell oxygen burning in a massive star. And I will describe it because I think this is important. So this type of, I would say, this type of code comparison efforts to give some kind of validity and credibility to those numerical simulations. So typically the setup is starting from an isentropic layer at the bottom, which has a given molecular weight and a mass fraction x0. And then you have above a stably stratified layer with another composition and a mean molecular weight mu1, which is smaller than mu0. And then you have a heat source at the bottom. Then looking at the different flow fields for a given resolution and for the 5 different codes, and then we have also a higher resolution for the same problem, then looking at the mass fraction in the bottom layer and the entropy fluctuations in the vorticity and the vertical velocity. And I will show the movie just to show you actually the complexity of the flow. So you will see it will start very rapidly, so be tuned. So 3, 2, 1, let's go. So you can see entropy fluctuation starting, and then very rapidly the flow gets a complex regime in the convective region. And what you can see is that, of course, visually there are some differences in those due to the different codes with a different approach. But most importantly, and I think that's the main conclusion, is that there is an excellent statistical agreement. I will stop that if I can. Yeah, there is an excellent statistical agreement regarding various Greek quantities, which are, for example, if you look at fluctuations, if you look at average fluxes of kinetic energy, of heat, of entropy, and if you look also at the mass entrainment rate, which is very important because this is, for example, what you need to do the 3-to-1 link. So I think that's a very, very good result to know that on a statistical point of view, that all those different codes converge on a complex problem of turbulent convection. So now this brings me to the 3-to-1 link, which is very, very important. And when I say 3-to-1 link, actually, I mean 2 things. I mean 3-to-2, and I mean 3-to-1. So let me explain myself. So when I mean 3-to-2, first of all, I think it's important to have discussions of 3D versus 2D, which means when should we use 2D, when should we use 3D? And the problem is that 3D simulations are computationally very expensive. Therefore, 2D simulations remain useful. And there is a nice discussion about that in the review by Kupka and Mulzam in 2017 in the Living Review for Computational Astrophysics. The cons for 2D simulations is that if you have turbulence, then we know that 2D actually is giving an inverse cascade of turbulent kinetic energy, which means that the dissipation is going from small scales to high scale. So it's inverse compared to the 3D, say, real cascade of dissipation of energy, which means that flows, the small scale structure, the description of small scale structure in 2D will be different from 3D. Also, 2D is certainly not appropriate when you actually break the symmetry, like in rotated system or MHD systems. And obviously, MHD processes are inherently 3D. And 2D is not appropriate neither for fingering convection, for example, as shown by Pascal Garot and Nick Brummel recently, just because fingering convection is, for fingering convection, what is very important is dissipation at the small scales. But there are pros for 2D because this allows you to explore parameters, to explore resolution, boundary conditions, simulation volumes. And for example, we have shown recently in simulations, in comparing 2D and 3D simulations, we have shown that actually different setups may result in more differences than the dimensionality if you're looking at large-scale convective flow structures. So this means that the exploration of parameters is really very, very important in those multi-simulations. And also, as has been shown recently by Edelman and collaborators in the study of waves generating by a convective core, the properties of internal waves are rather similar whether you study them in 2D or 3D, particularly the frequency spectrum of the kinetic energy. So those are, I would say, real advantages. And I may suggest that 2D versus 3D may be a topic to discuss during the panel discussion after the talks of this morning.
About 5 more minutes, Isabelle.
Yeah, okay, fine. So going from 3D to 1D now, I would say this is very important. And there are two major motivations for 3D simulations. First of all, obviously, this is to improve the physical description and the understanding of relevant processes you are interested in. But also, this is to improve the treatment in 1D stellar evolution codes, that is, improve formalism or constraint-free parameters. And this is crucial because this is the only way to make the link between 3D simulations and observations through the 1D stellar evolution codes, because you can then compare 1D stellar evolution code results directly to observations. And therefore, you can constrain and validate your 3D simulations by establishing this link between 3D and 1D, and eventually with observations. So here I just want to give some examples of how to build this link. And there are several ways to analyze 3D simulations and to derive quantities that can be implemented in 1D stellar evolution code. So first of all, you can determine, and I will focus more on mixing with, for example, determination of diffusion coefficients to describe mixing. So you can use, for example, tracer particles. And there is an example with the study of chemical mixing induced by waves by Rogers and McElwain, where you have an initial distribution of particles. Here, those are the white dots. And after some time, you study the particle trajectories. And from there, you can infer a diffusion coefficient as a function of the radius in the stellar interior. And you can directly implement this diffusion coefficient in a 1D code. You can also determine what I call statistical diffusion coefficients, as we did based on the idea of Jane Pratt, using extreme value statistics, where you consider that the mixing is driven by the most extreme penetrating plumes, and you can derive the probability distribution of those penetrating events. And from there, in the framework of a statistical theory, which is the extreme value theory, you can derive a diffusion coefficient as a function of the radius. And then you can apply that to 1D codes, as we did here, to study consistently the lithium depletion in solar-type stars. You can also derive from multi-simulation entrainment rates to describe the growth of a convective boundary. And this is based on the idea, looking at this schematic drawing from Mekin and Onit in 2007, where you have a convective core and you have a turbulent boundary layer, which actually slowly diffuse, and where the mixing in this boundary increase and increase, resulting at the end in an increase in mass of this boundary layer, and therefore an increase in mass of the convective boundary. And you can describe this mixing by an entrainment rate, an entrainment law, which depends on the convective velocity at the boundary and on what we call a Richardson bulk number, which describe the stiffness of this boundary. This is typically the strength of your turbulence in terms of its kinetic energy proportional to V square, and the variation of the buoyancy in this boundary layer characterized by the Brun-Weisseler frequency. And these entrainment rates have have parameters that actually can be determined by hydro simulations. And recently, those entrainment rates has been applied in 1D stellar evolution models for a very broad range of main sequence stars by Laura Scott and collaborators. And what is interesting is that the entrainment rate, as defined here in red, will depend on the convective velocity. And as I told you, the convective velocity depends also on the luminosity. And therefore, because convective velocity increase with luminosity, and because luminosity increases with stellar mass, entrainment rate will increase with the stellar mass as well. And this type of relation can explain the observed mass dependence of convective boundary mixing. But the problem and the difficulty is that in order to reproduce observations, then the constant A in this entrainment law requires to be much, much smaller than the values inferred from numerical simulations. So there is more work definitely here on this aspect of entrainment and more things to understand about how this process is really working and how this can be applied to the stars. And then you can also...
Isabelle, we're getting into the question
in
time.
2 minutes,
So.
okay.
Okay, cool.
I'm almost done, 2 minutes.
Perfect.
Yeah, so, and then we have also the possibility to determine overshooting distances based on radial velocities profile or vertical kinetic energy. And for example, here I quote example of the work by Corey et al. Or Kai, where you use autocorrelation of radial velocity, and you look at the behavior of this correlation, which is the product of radial velocity and the radial velocity at the convective boundary. And at the second zero, you define an overshooting distance. So this is a way to define this overshooting distance. Or you can do it as well, as we've done recently, based on the distribution of maximum depth of penetration plumes, and then your time average will define an effective width of the overshooting layer. If I give all those examples to show that it's not straightforward to interpret numerical simulations, and you have different tools for that, different methods, different statistical approach in order to get the, I would say, the best of those numerical simulations and then establish this 3-to-1 link. And I will finish here with my conclusion and perspective. First of all, I would say my conclusion is that definitely 3D stellar hydrodynamic simulations have reached maturity. And it's very reassuring to know that different codes with different approach give similar statistical results on a very complex problem. There are now increasing number of studies which encompass a broad range of stellar masses and stages of evolution, from low mass stars to massive stars, from pre-main sequence to late stages of evolution. And those hydrodynamical simulations provide more and more constraints on 1D formalisms and on free parameters. So this is very, very promising. There is a challenge, as I mentioned, this is extrapolation of results from multi-D simulations to the stellar conditions, whether your simulations are in a pseudo state, so not thermally relaxed, or whether your simulations are artificially boosted with an increase of the luminosity. And then the future challenge is, I think there is still a lot of work to do to understand impact of rotation and magnetic fields on transport, which is either mixing or angular momentum. And well, things are going to move in the community, and this is, I think, one of the main challenges for the future. And I will stop here. Thank you very much. I'm happy to take any question.
Okay, questions for Isabelle?
This is Adrian Fraser. Thank you for a really nice and comprehensive overview. That was great. This is maybe a naive question. I've only ever worked with fluid codes where we've got explicit diffusivities, and so I know that a lot of care goes into making sure in some of this other work that the errors due to resolution stuff are diffusive, and so you can have a lot of well-behaved turbulence because of that. A lot of the stuff you talked about today depends on ratios of diffusivities, like the Prandtl number, the magnetic Prandtl number, for like dynamos or meridional circulation and stratified shear flows. Is that something that you can vary in these codes, or is that sort of baked into the scheme? Does the question make sense?
It makes sense. I would say that it's more or less embedded in the scheme. So it all depends. So, some codes, for example, if you rely on the implicit logic dissimulation, then it's really relying on the scheme. So you'll rely on your truncation errors to define your I would say, your viscosity or your numerical viscosity. Some of the codes actually are using an artificial viscosity where they can more or less control I would say, the prime number, for example, and but it also depends on the numerical diffusivity of their own code. So it's not a fully controllable parameter, and therefore you have to be very, very careful there. I don't know whether I answered to your question.
You did. Thank you.
Hi, this is Matthew Ranso. I was wondering regarding the 2D simulations that can still be used to do parameter studies and inform us. You mentioned that these should not be trusted for small scales. I was wondering if you have like some rule of thumb based, I don't know, on the size of the domain for down to which scale I can trust 2D and below which I should really not look at it.
I think that's a difficult question. I think it's more about whether you are interested in the dissipation at small scales or whether you are more interested in the large scale. For example, the largest eddy for convection, and you do not really care about what's happening in terms of the dissipation at the very small scales. So it really depends on the type of problem you are looking at. I don't think there is an easy rule of thumb, because if you look at the problem, for example, of fingering convection or tourmaline convection, their dissipation at small scales is absolutely crucial. So it means that you need to be able to describe this dissipation, even down to the viscous dissipation, correctly. So I don't think there is really a rule of thumb there, and it really very much depends on the type of problem you are looking at. If you're looking at the ballistic problem of penetration, for example, of convective penetration, then with those extreme events, this is more a large-scale problem. So the treatment of the small scales is not so crucial. And therefore, you may not have so much differences between 2D and 3D. And this is actually what we've been seeing in the Pratt et al. 2020 study.
Okay, thank you.
It's JJ Zanesi, CETA Research Associate. Yeah, thank you very much. I really liked your talk. So I was wondering if you could comment a little bit more on the danger of using an artificially enhanced luminosity. Is the issue that buoyancy waves within the radiative regions will be rapidly damped, or is it something else?
Not rapidly damped. So I think the main problem is that, as we have shown in this very recent study in the Baraffe et al. 2021, is that you actually force your convection. So you increase the convective velocities. And therefore, what happens is that you can see the system evolving more rapidly and departing more from your initial conditions, which means that if you were able to simulate boosted model over quite a long time, then actually you will end up with a system which is quite different from the initial star or the initial model you had. So that's one of the first problems. The second problem is that for the waves, for example, angular momentum, I would say lows or transports depend on the damping of the waves, and the damping of waves, which is due to radiative damping in stellar interiors, depends on the frequency of the wave at the power of -4. So low frequency waves are more damped than high frequency. And it is because of this damping, then you can actually drive mixing and angular momentum. So depending on the spectrum of your waves and where most of the energy is, then you're going to change also your efficiency of transport of angular momentum. So if you increase your luminosity and therefore shift the spectrum of the waves toward higher frequency, you're also going to change the efficiency of the transport of angular momentum. So you may end up with some transport coefficients for the angular momentum, for example, of description, which is actually not realistic. So that's one of the problem we want to point, which is that you change the physics of the waves and you change the property of the waves. You may even change their observable signature at the surface, just because you change the range of frequency, which is relevant for the given luminosity. So that's the problem.
Hi, Vicky Antoci here. Very nice talk. Thank you very much. I have a question that may be very silly. I honestly don't know. To my knowledge, convection changes very much with metallicity. So could you maybe comment how this is being implemented in 3D models? And especially if you kind of, how is it done? Do you have like all the elements that you would find in a star, or, yeah, I hope it makes sense what I'm asking.
I think I understand, yeah. All questions make sense. It's only the answers that do not make sense sometimes. But I think the metallicity in the 3D simulations, I mean, you can decide what metallicity you want to study. For example, there are studies of convective cores for solar metallicities and the studies of convective cores of low metallicities. What has not been done so far, but anyone can react if I'm wrong, we have not really looked or explored the impact of metallicity on, I would say, really the convection properties. That is, looking at the convection properties in a specific core, convective core for a specific mass as a function of the metallicity. Such exploration has not been so far. It may be a bit complicated because when you change the metallicity of the star, you change its luminosity. And if you change the luminosity, as I mentioned, you will change as well the convective velocities. So in a sense, because of this typical relationship between convective velocity and luminosity, you can maybe kind of extrapolate somehow what would be the impact of metallicity on the convection because of the change of the luminosity due to the metallicity. And after, I think it's quite a complicated question because it all depends on what you want to compare. Do you want to compare stars with different metallicities with the same age, or stars with different metallicities with the same luminosity? You will get different answers in terms of the convective properties, just because you're changing the luminosity. But all in all, I would say that this is still something that needs to be investigated, which is really the impact of the metallicity on the properties of the convection and properties of the overshooting as well. And this will come because, as I said, more and more groups are working on exploring stellar parameters.
Hi, this is Liam O'Connor. You
Yes.
mentioned that we're starting to get agreement between different codes when studying the same systems and how that inspires confidence. Can you talk about some systems where that's not the case and what the challenges are there?
Well, this is the first time that codes have been compared on such a complex problem. So, so far we have not found yet, because I only have one point in my diagram. And all those codes that I've mentioned are, of course, benchmarked to, I would say, typical hydrodynamical benchmarks, which are kind of ideal tests. But for example, something that would be very interesting to do, and we have been talking about that, would be to compare also the wave properties in those different codes. And maybe the answers will be different or not. So I cannot answer because so far, as I said, this is the first real code comparison project on a complex problem. And so far agreements are good. But if we continue comparing those different codes and different approach, we may find indeed problems which lead to disagreements. We'll probably find some. And waves may be an example.
Hi, Isabelle. This is Jim Fuller. So you mentioned the really slow Mach numbers associated, really low Mach numbers associated with meridional circulation. I was wondering if anybody has tried to simulate meridional flows, and if so, what we learned.
In realistic conditions, no, just because 10 to minus 8 is a real problem.
Sure.
And so I don't know. Actually, we tried, and it's just unreachable. So there are different ways of doing it, which is then increasing the rotational velocity, and therefore you drive more meridional circulation. But that's a bit dangerous because then you may have other effects and star deformation. So actually, no, I don't really know who has really tried. And I think it's an interesting discussion to have how we could, with existing hydro simulations, existing codes, how we could try to model this meridional circulation, which are in stars have such low Mach. And maybe we could define a framework where we could understand better this meridional circulation and the rotational mixing, and then extrapolate that to stellar conditions. To say the truth, I haven't found a solution yet. Maybe some people have. I don't know. But I think this is the real challenge, and probably this is why so far people have left somehow the rotational mixing with hydro simulations just because of that.
Okay, thanks.
Pascal, do you want to address something about meridional circulations?
Yeah, maybe. I think the only thing I would say is there are some attempts to model meridional circulations in a quasi-steady framework, as in instead of doing an evolution code, you look for relaxed quasi-steady solutions of the governing equations that exhibit these meridional flows. And there's a long history of trying to do that in the field. The difficulty there is that when you look for quasi-steady solutions, then everything matters. You know, there's no, everything participates in the final force balance, including viscous forces if you're not careful, because you assume you have reached this quasi-steady state. So, and in stars, presumably viscosity doesn't participate much in the driving of the meridional flows. It's probably more thermal driving or driving through other processes. So you have to be very careful to be in the correct parameter regime where the viscosity is not important. And in particular, you have to make sure your boundary conditions don't artificially drive viscous flows, because otherwise, you know, in rotating systems, you have Ekman flows that will exist. And so you need to make sure their importance is negligible in comparison with other types of driving. So the answer is yes, there is, but it's very difficult. And I think we're still far from doing it in a way that can be easily implemented in stellar evolution codes.
Okay, we might have time for one more really, really quick question. And if not, let's all thank Isabelle again for the great talk.